Hi guys, welcome to JIK 224 E-Kuliah series. I'm Dr. Sumia, and this fourth video still in chapter 1, which is structure and stereochemistry of alkene. So in previous video we have looked at the conformation of monosubstitute cyclohexane. So in this video we will cover conformation of disubstitute cyclohexane. So upon completion of this topic, you should be able to draw ring flips of cis and trans stereoisomers of disubstitute cyclohexane and predict the most stable conformation. So disubstitute cyclohexane such as 1,4-dimethyl cyclohexane has cis and trans stereoisomers. Okay, so here we have trans 1,4-dimethyl cyclohexane where the methyl group, two of the methyl groups are in opposite direction. So this one methyl group is facing towards us and one methyl group is facing behind. Okay, and then we have the cis 1,4-dimethyl cyclohexane where both of the methyl group are facing the same direction, which is towards us. So each of these stereoisomers has two possible chair conformation. So a total of this, we should have 4 chair conformation. So to draw the chair conformation, first draw one chair form and add the substituent. So pick 2, because we are talking about 1,4-dimethyl cyclohexane, so you can pick 2 carbon located at 1,4 to each other. So this is carbon number 1 and this is carbon number 2. So the trans isomer must have one group above the ring and an up bond and one group below the ring on a down bond. Okay, so because trans is in opposite direction, we should place one carbon up and one carbon down. And then we can add the substituent. Okay, we can either place the substituent at axial position or at equatorial position. Okay, because in this example we place the substituent in axial position, but it is still a trans because one of the methyl group is facing up and one of the methyl group is facing down. So now we have 2 groups in axial position. So this is called diaxial. Okay. Step 2, ring flip the cyclohexane ring. Okay, now we flip the ring. The up carbon flips down. Okay. Now we become down and the down carbon will flips up. And then we add the substituent to the second conformation. So ring flipping converts axial bonds to equatorial bonds and vice versa. So the diaxial methyl group will now become a di-equatorial because both of this methyl group are now in equatorial position. So it is still trans because one methyl group is above the ring, okay, here on an up bone, and one is below on a down bone. Okay, so ring flipping does not change the cis and trans isomer. It will only change the position of the substituent, either in equatorial or axial position. A cis isomer has 2 groups on the same side of the ring. So this just now we discussed about the trans isomer. So now the method to draw the cis isomer is similar, but a cis isomer has 2 groups on the same side of the ring. So either both up or both down. In this example, conformation 1 and 2 have 2 methyl groups drawn up. So here we have one of the methyl group up but in equatorial position, another methyl group is also up but is in axial position. So when they flip, okay, the axial methyl group here will become equatorial, while the equatorial methyl group here will become axial. But this conformation is still a cis isomer. And both conformation have one methyl group axial and one in equatorial position. And they have relatively the same amount of energy. So a disubstituted cycloalkanes or cyclohexane, a cis isomer has two substituents on the same side, either both on up bonds or both on down bonds. A trans isomer, on the other hand, has two substituents on opposite side, one up and one down. And whether substituents are axial or equatorial depend on the relative location of the two substituents on carbon 1,2, 1,3 or 1,4 and so on. Let's look at another example, which is cis-1,3 dimethyl cyclohexane. So in this case, the methyl group will be at position carbon number 1 and carbon number 2. So cis-1,3 dimethyl cyclohexane can have both methyl group in axial position or both in equatorial position. So the conformation with both methyl group being equatorial is more stable. In conformation number 1, we have both of the methyl group in axial position or diaxial. Is very unfavorable because it has the 1,3 diaxial interaction. When it flips, the methyl group will convert to equatorial position. So now we have di-equatorial position, which is much more stable as compared to the diaxial position. You can see here that the methyl group are further away from the 1,3 diaxial interaction. It has more room here, further away from the. It is less crowded and has more rooms. What about the trans isomer? Okay, in trans isomer, both conformation have one axial and one equatorial methyl group. So they have the same energy because they are present in almost the same amount. Okay, or equal amount. So either way, when you flip, you can have one equatorial methyl group and one in axial position. What about for cis-1,4 di-third butyl cyclohexane? Okay, now we have two groups of third butyl groups, which is a very big group or a bulky groups. So in this case, the most stable conformation of cis-1,4 di-third butyl cyclohexane is the twist boat. Okay, why? Okay, both chair conformation will require one of the bulky third butyl group to occupy an axial position. So they will force the third butyl group at axial position will be forced out, okay, to interconvert to the twist boat, so that both of these third butyl group is in equatorial position. Okay, because if in this case we will still have the 1,3 diaxial position interaction between carbon number 3 and carbon number 5. Okay, let's look at this example. Draw both chair conformation of cis-1,2 dimethyl cyclohexane and determine which conformers is more stable. Repeat for the trans isomer and predict which isomer, cis or trans, is more stable. So for A, we will have one methyl group in axial position and one methyl group in equatorial position. Okay, at carbon number 1 and carbon number 2. So when the ring flip, okay, the carbon at axial position will transform into equatorial position, and the methyl group at equatorial position will convert to axial position. So each of these conformations places one methyl group in axial position and one methyl group in equatorial position, giving them same energy. Okay, for B, which is the trans isomer, we would have one conformation with both of the methyl group in axial position, and when it flips, we have both of the methyl group in equatorial position. So this is diaxial, so we will have a higher energy because there is a 1,3 interaction, 1,3 diaxial interaction. And then for this one is the di-equatorial position, it has lower energy, so it is the most stable conformations. Okay, the trans isomer at di-equatorial position is the most stable conformation out of all the 4 conformation. We have example number 2. Draw the most stable conformation of trans 1-ethyl 3-methyl cyclohexane. Okay, so now we have 2 different substituent, which is 1-ethyl and 1-methyl group. Okay, as the solution, first we draw the 2 conformation. Okay, placing because here it says carbon 1 we have ethyl group, so you have to place the ethyl group at carbon number 1 and methyl group at carbon number 3. Okay, so one in position at axial position and one in equatorial position. So the ethyl group is bulkier than the methyl group, so the conformation with the ethyl group in equatorial position is more stable here. Okay, it's less crowded here. So as a summary, chair conversion or ring flips convert axial to equatorial and vice versa. Ring flips, however, cannot change their cis-trans relationship. A cis isomer has 2 groups on the same side of the ring, either both up or both down. A trans isomer, on the other hand, has 2 substituents on opposite side, one up and one down. This is the reference, and if you have any question, feel free to contact me at my email address. Thank you.